Okay, so before we get in with today's content, I entered in all of the grades yesterday. So that meant going through the quizzes and writing down your highest score and looking for your screenshot from that practice website and using those two things to give you your practice and application grade, and then going through Edpuzzle and the exit tickets to give you your participation grade. The last thing I need to do is look at the Flipgrid and assign extra credit points for those people. Last time I saw it was Andy and Asha, but I think a couple other people were going to try it. I haven't looked since Sunday.
I Miss Baskin.
Okay, cool. I figured a couple more people would. So
did you finish grading it?
What?
Did you grade it? Because I did it before the due date.
No, I haven't. Yeah, I haven't looked at it since Sunday morning. So that's one thing I didn't get to yesterday that I'll do today. So I'll enter those extra credit points in today.
Okay.
If you turn in something late, are you taking off points?
No, so there are no points taken off for late stuff in term 4. Just know that it might take me a couple of days to catch it. Unless you send me an email or a message that says, hey, I did this thing, and then I'll go. But like I looked this morning and I updated a bunch of stuff from all my classes this morning that people had done. But after that, I probably won't check again until the end of the week to update people's stuff. But I've been making like meticulous paper notes of when stuff is done, as well as the notes in the comment box, so that we can all, so that way hopefully I won't miss something. But if I do miss something, please let me know, because I do want to give you credit for everything that you do. So with that being said, this week starts us on the first of our material that I did not give you before we left. So what you saw in the participation assignment this week is I attached both a PDF and a Google Doc of the notes we're going to do this week. And so that way, if you had a printer, you could print them off and treat it like anything else. And if you don't, because a lot of people don't, or you have a printer that has no ink or a printer that has no paper, then you could type your stuff into the Google Doc, or that might be kind of awkward while we're doing this sort of setup. So you can, you can take screenshots or pictures and then fill out the stuff later, or write things down on paper. But again, all the notes are notes. They're your notes. They're not to turn in for me. But they're going to make the rest of everything we do infinitely easier if you have something to refer to. So, and we'll talk more about that later on. Okay, so let's get started. Looking at exit tickets last week, I have multiple people asking, why are we doing electron configurations? What is the point? What is the purpose? And I would say the purpose of them is that they're going to tell us exactly where in an atom all of the electrons specifically are. And that is something we need to know, because we need to know where each and every single electron can be found, because only some of them are important. And we want to be able to find the ones that are important and ignore the rest. So electron configurations are going to give us the address, the very specific place to go and look inside an atom to find the electrons that are actually important, because it's only this last small little subset of electrons that are actually involved in chemical reactions. All of the other electrons in an atom are just there, but they don't actually participate in any chemical reactions. So it's kind of funny that way, but we do care about a very specific subset of electrons. These things are called valence electrons. And I think a lot of people have maybe heard that term before in 8th and 9th grade, with some sort of definition for them, but without a deeper explanation of what it is they are. So today we're going to be talking about valence electrons specifically. So I am going to switch over on my iPad to, these are the notes that were from the participation. So however you plan on doing this, whether it's notebook paper or the Google Doc or the printed out PDF, you do you. You might also want your periodic table, although I did, cut this one small picture onto the note sheet there. But get yourself situated, and I will switch over to my iPad. Okay. So, as I said, not all electrons are equally important. The electrons that spend their time farthest from the nucleus, which means those that have the biggest value of N, which was our energy level number, otherwise known as the biggest big number. So we're looking at the electrons in the biggest big number energy level. These are the ones that are important. Because they're the ones that are actually going to form chemical bonds when they bump up against other atoms. These are the ones that can be taken when you are talking about a chemical reaction, and these things are referred to as the valence electrons. So basically, the study of chemistry is the study of what is happening with the valence electrons. Like, that's kind of what dictates the behavior of every single type of element and what happens in chemical reactions. So we already kind of looked at that at oxidation and reduction, but this is just going to bring it home even more. So because of, the weird overlap that we sometimes have in the electron configurations, that 4s comes before 3d, those outermost electrons are not always the highest energy, but they are going to literally be the farthest away. They are going to be on the outside. So technically, our valence electrons are the outermost electrons. They're always going to be electrons in S and P. They will never be D and F. Because before you write a D or an F sublevel, there's always going to be an S with a higher number. So you're always looking for the biggest big number when you're looking at valence electrons. But if I can only have valence electrons coming from the S sublevel or the P sublevel, what is the maximum number of valence electrons that you can have?
6.
6 is going to be from P, but how many can S have?
2, so 8.
2.
So it's a max of 8. And sometimes that number sticks in people's head, like that they know that from somewhere, but you're not sure where, and this is where. So you can get 2 valence electrons from a S sublevel and 6 valence electrons from an 8 sublevel. From a P sublevel for a total of 8. So when we're looking at an electron configuration, you can just find those outermost electrons and identify what they are. So let's do some of these. So arsenic's electron configuration here. It was number 33, if I remember correctly. So arsenic, if we're doing the short form, would have argon, 4s2, 3d10, and then 4p3. So that's its electron configuration. So when you look at that electron configuration, what is the biggest big number in that configuration?
4. 3d10.
4. There's a 4 right there and a 4 right there. The 3 in the middle is smaller. It does not count. So those are my outermost electrons, and arsenic would have 5, and I refer to them as VEs, valence electrons, because that is a lot less to write than valence electrons. So I am skipping the 3D because 3 is a smaller number. Are you with me?
Question.
Yes.
Will it lose electrons from the P or the S first?
P, but arsenic will actually gain instead of lose.
Okay.
Yeah.
Thank you.
Uh-huh. So copper with 29 would be argon 4s2 3d9. So for copper, what is its biggest big number?
4s.
The 4s, right? So it's also, I am ignoring the 3d because that is not the outermost thing. The 4 is the outermost thing. So copper has 2. Easy enough. So calcium, argon 4s2. Well, that's super easy. How many valence electrons does it have?
2.
2. And that is one thing that is helpful about writing this shortened condensed form. What you'll notice is basically the thing outside of the brackets is primarily valence electrons, right? So it allows us to really focus in on only the things that count as long as we ignore the d electrons. Let's do krypton. I'm not going to cheat and write krypton in brackets. I will still put argon in brackets, but it's 36, so 18 plus, that's 20, 30, 4p6. So how many valence electrons does krypton have?
8.
It has the full 8, right? 2 from there, 6 from there, for 8. And then let's do oxygen, and let's write out oxygen's full electron configuration because that's easy. So it's got 8 electrons total. So 1s2, 2s2, 2p4. So how many valence electrons does oxygen have?
6.
6. Because I get to count both of these are the biggest big number. 2 from there, 4 from there, 4, 6. And then if I do sulfur, sulfur has 16. So let's do 1s2, 2s2, 2p6, 3s2, 3p4. And sulfur's outermost energy level would be what?
3.
The 3, it's both of the 3s. So how many valence for sulfur?
6.
All right. Selenium, let's see here. Selenium is 34. So let's cheat on this one. Let's do argon, 4s2, 3d10. So that's 30, 34. So how many valence electrons does selenium have?
6.
6. So if you look on your periodic table, and we can cheat and look at this one down here just a little bit. So we just did oxygen, sulfur, and selenium. And all of those had how many valence electrons?
6.
6. So where is tellurium on your periodic table?
Right below selenium.
It is right below selenium. I did not have that chunk, but it is right here. So how many valence electrons do we think tellurium is going to have?
6.
It will have 6. So there is a handy thing here that goes together between the periodic table and our valence electrons. So oxygen, sulfur, and selenium are all in the same vertical group. So they're all in the same vertical group, and they all have the same valence electrons. That makes your life much easier. Okay. So it says, since the periodic table is organized by electron configuration, and we use the electron configuration to figure out the valence electrons, it should make sense that the periodic table can be used to give us information about the valence electrons. So what we're going to find is that the periodic table is going to become a super handy thing for us.
Ms. Baskin,
Yes.
I have a question.
Yeah.
So on the periodic table, you know those 2 rows of elements at the bottom,
Yes.
how like they continue, but like it's like a almost like abbreviated kind of continuing. So would nobelium be in that same column since?
No.
No.
So yeah, so it's really weird. The way the periodic table should look is that and that small bottom section is where those elements are, nobelium and such. So we don't normally show it this way, but those 2 bottom rows that are in the F block don't actually get counted as with any of the main 18 groups. They're just kind of standalone. They don't have group numbers. So it's a little different. They technically all would have 2 valence electrons because all of them technically have an S that fills before the 6F or the 7F. So that's kind of a thing there. But for the most part, we ignore those elements down there unless we're talking about radioactivity.
Okay, thank you.
Okay. So we started with electron configurations. Then I taught you how to do the shorthand version where you use the noble gases. But now I'm telling you that we actually only care about the valence electrons, and the valence electrons are only a small portion of the electron configuration. So we're going to condense this down into yet another shorthand that is going to be even easier. So this guy, Gilbert Lewis, proposed a symbol notation that would represent only the valence electrons, because ultimately all we care about in chemistry is the valence electrons. So that way we don't have to deal with the entire electron configuration. These things are referred to as Lewis diagrams, because when you get to come up with something, you get to name it after yourself. But they're also just referred to as dot diagrams. And I have a feeling that some people may have done these or seen these before. Dot diagrams are easy. So when you do a dot diagram, they're called dot diagrams because you represent the valence electrons as dots. And we do have a maximum number of valence electrons, which as we said above is 8. So that is also the maximum number of dots, is 8. And if you think of an element symbol like we see here on these boxes, we think of it as having 4 sides. So if you've got 4 sides to an element symbol and you have 8 dots, how many dots are you going to put on a side?
2.
2. Okay. So you start by placing the dots in the middle of the side of the element symbol, and you follow the empty bus seat rule, which for us means you put 1 dot on each side, and that takes care of the first 4 dots because there are 4 sides. And then your valence electrons 5 through 8 are then going to pair up next to the first ones. So X here is a generic symbol, but essentially you would go, all right, so here's my generic symbol, dot 1, dot 2, dot 3, dot 4, because empty bus seat rule, each dot gets its side, and then dot 5, dot 6, dot 7, dot 8. Now, I go in clockwise order and start from the top because it's habit. It does not actually matter though. you could go 1, 2, 3, 4, 5, 6, 7, 8. Does not matter. It's just kind of the pattern that we end up doing. So I want to look at this section of the periodic table here and actually fill in some more information then about the number of valence electrons, as well as what the generic dot diagram would be. So if I look here, so we said that the oxygen, sulfur, and selenium all had 6 valence electrons. I would like you to notice that this is group 16. How many valence electrons do you think fluorine, chlorine, and bromine have?
7.
7, because it's in group 17. So with the exception of helium, how many valence electrons do neon, argon, krypton on down have?
8.
8, because it's basing it off of the group number. But how many valence electrons would helium have? Can't have 8.
2.
It's got 2. So then working our way left, nitrogen, phosphorus, arsenic, and that whole group is going to have how many valence electrons?
5.
5, because it's based on the 15. Carbon, silicon, germanium,
4.
4. Boron, aluminum, gallium on down.
3.
All right, we're going to skip this D block and come back to it in a second. So beryllium, magnesium, and calcium.
2.
2. And hydrogen's column
1.
is going to be 1. So this entire section, and this pretty much applies for both the D block elements as well as what Josh was saying, the F block below them. All of these, before you write 3D or 4D or 6F, there's always an S beforehand. So all of these tend to also have 2 valence electrons. There are a couple of weird exceptions in there. We don't deal with the realm of exceptions at this point. So you can basically think of it as your valence electrons are your group numbers. So 1, so we get to kind of go 1, 2, all the way across. So groups 2 to 12 are all 2. And then 13 is 3, 14 is 4, 15 is 5, 16 is 6, 17 is 7, and 18 is 8, with the exception of helium, which is only 2. So if you look at it this way, this is exceptionally easier than writing out electron configurations. It tells you exactly how many electrons you need to care about in terms of the next idea being like, what's going to make bonds? How do these things do stuff? And then the other thing that we can do is then use those number of valence electrons to do a dot diagram. So we can just do the dot diagram for the first element in each one of these. So hydrogen, lithium, sodium, potassium, they all have one valence electron, so they're only going to have one dot. It honestly does not matter what side you put it on. I'm going to start maybe by actually putting it on the side. So hydrogen's one dot would be that. That's its dot diagram. H with a dot. But beryllium should have two dots. So the only thing you have to remember about beryllium is you cannot put the dots side by side because that would violate the empty bus seat rule. So dot 1, dot 2, 2 dots. That would also hold for all of these guys in the middle. Boron should have 3 dots. 1, 2, 3. And then carbon's column is the first one that's going to have a dot on every side. So 1, 2, 3, and 4. Nitrogen with 5, you're going to go 1, 2, 3, 4, and then the 5th dot pairs up with the first one. And oxygen 1, 2, 3, 4, 5, and then 6. Fluorine, you recognize, is going to have 1, 2, 3, 4, 5, 6 with a 7th dot by itself. And then the noble gases are all filled up, completely surrounded by dots, which kind of indicates that the noble gases don't need anything. They have all their dots. And since they have all their dots, that's kind of why the noble gases do not react. Helium with its 2 valence electrons is going to be the one exception to that empty bus seat rule. Its 2 dots are going to go side by side because they represent a full energy level, right? This represents the first energy level, which only has the one S. So that's why they get to go side by side. But which do we prefer, dot diagrams or electron configurations? Which one's easier?
I think it depends.
Well, we're going to end up using dot diagrams much more frequently. So we'll put it that way. So if you need to, take a picture of the annotation that I did on that periodic table, because you're going to want to be able to have that as well, because then you can just get that for literally any particular element. So I'll give you a minute if you need to snap a picture of that.
Ms. Baskin,
Mm-hmm.
when we send these our work to you, do we send it as a PDF?
You're not sending this work to me. These are your notes.
So we don't have to show you them?
No, but you're not really going to be able to do the graded stuff if you don't have them, unless you have a really good memory.
Oh, I thought you were checking them.
No, you're doing enough stuff. I don't need to check this too.
Can you scroll up just a little bit real quick?
Yes.
A little bit more.
Mm-hmm.
Yeah, thank you. It's like 2.
Okay. So let's move on to the next page. And I just want to start the next thing. So the next thing is called photoelectron spectroscopy, which is a really big name. But it is basically a lab experiment that tells us that everything that we're doing right now, we actually know is correct. So this is what we'll finish up on Thursday, but I did want to start it today to make sure we had enough time on Thursday. So all these notations and patterns are nice, but how do we know they are correct? because we can prove it using photo electron spectroscopy. Okay. Photoelectron refers to basically electrons interacting with light or light energy. Spectroscopy is anytime you see the word scopy, you can imagine that that is some sort of measurement. All right. So this is a way to measure these things. And it was this experiment in the 1950s that provided evidence of not just energy levels, but the sublevels. All right, so this provided us with the information that it's not just energy level 1 and 2 and 3, that in 2, there are actually 2 sublevels, 2s and 2p. And it also justifies that filling order, meaning that this is what proves that 4s does in fact fill before 3D. It was this level of experiment that does this. So what this is you can imagine, in some ways it's kind of similar to the mass spectroscopy that we did, but instead we're talking about electrons here. We're trying to measure the number of electrons. So what you do is you figure out how much energy is required to pull off electrons. So you can imagine that's essentially like, you know, those cartoons of like horrible evil children picking off the wings off of flies one at a time. It's like we're picking off the electrons from an atom one at a time and measuring how much energy does it require to pluck off an electron one at a time. Except atoms are small, so we do this with a larger sample of that at a time. And all of this isn't that so much important to be able to kind of know, except that how much energy is required to pull off the electron is going to depend on where it is. Okay. So what these things generate is a graph. And in some ways, it is a graph that is very similar, again, to that mass spectroscopy, where the size of the peak of the graph tells you how much stuff there is. But there is a difference. It's an unusual graph because it provides you, when you read it left to right, it provides you with the actual electron configuration. You can see the configuration in the peaks. They are, you can read it left to right and you will start seeing 1s and 2s and 2p, etc. So for these things, you have to recognize that the nucleus, you have to imagine that the nucleus is on your left side of your graph. So if it's on the left side of your graph, which electrons should be harder to pull off? The electrons that are literally right next to the nucleus, or the electrons that are far away from the nucleus?
Far away.
No. It is much, much harder to pull off an electron that is right next to the nucleus because they're so attracted. Remember, the nucleus is positive, the electrons are negative, they like each other. So if they're really close to each other, they're going to have a lot of attraction. So if you want to try and take away something that's that close, it will require a lot of energy. But also you have to remember that the closest thing to the nucleus is my very first energy level. So the first peak that is on the left of these graphs is always going to represent the 1s energy level sublevel. And the size of 1s, you have to remember, s holds how many electrons?
2.
2. So the size of this peak right here is going to determine the relative amount of electrons in all the other peaks. So if that first peak is 1s, that means that the next peak should be 2s, and they should be the exact same size. So that'll make more sense when we see one of these next class. So the other thing you have to remember is that bigger and bigger elements have more protons in your nucleus. And if you have more protons, that means you have more attraction. Because again, our nucleus is positive and our electrons are negative. Opposites attract. So the more protons you have in the nucleus, the more attraction there is, and that means that it will require more energy to pluck off electrons. So the other thing you're going to notice is that as you have more and more protons, all of your peaks start shifting left because more energy is required. One last thing to note is that when we have paired electrons, those paired electrons are negative. So if you try and shove two electrons right next to each other into a pair, what are they actually going to slightly do to each other because they're both negative?
Push.
They're going to push apart. So they're going to repel against each other because that's what like charges do. And if they're already repelling and pushing against each other, do you think that would make it easier or harder to pull one off if they're already pushing against each other?
Easier.
Easier. So it requires less energy to separate them. So we'll talk about all of that in more detail on Thursday. I'm just kind of laying some groundwork here. So I'm going to look at the rest of this page and that'll be it for today. So if I look at this little model of lithium, right? Lithium has an atomic number of 3. So I know it's got 3 positive protons in there and it's got 1, 2, 3 electrons. So between electron number 1 and electron number 3, right? Which one is going to require more energy to remove? 1 or 3?
1.
1. Because why?
It's closer to the nucleus, so the attraction between the protons in the nucleus and electron 1 is stronger than for electron 3.
Exactly. So what if we compare, so we know that 1 is going to require more energy than 3. What about comparing 1 and 2?
They're going to be the same.
They will be the same. They're going to have the same energy because they're the same distance away. So basically what we can say is 1 is equal to 2, and they are both greater than 3. If we look at the amount of energy required to remove, right? 1 and 2 are going to be the same because they're the same distance, and they will both require more than number 3. Okay, so this is what one of these spectrums looks like. So our x-axis is given in kilojoules per mole. All right, and kilojoules is a unit of energy, so that's what we're talking about, the energy needed to remove. But I do want you to notice the numbers and tell me what is unusual about this x-axis.
It gets smaller.
It's backwards.
It's backwards. It's getting smaller. Okay, so it starts big gets smaller. Because again, we have to remember that our nucleus is right here. That's where we have to imagine the nucleus is, because it takes more energy to remove the closer you are to the nucleus. So this 10,000 number is right next to the nucleus, because if you were right on top of the nucleus, it would be so much attraction, it's really, really hard to pull it off. So which of these peaks, this first one or the second one, represents electrons that are more tightly held? The one at about 6,000 or the one at like whatever that is?
6,000.
Right. Because the energy value is larger. All right, more tightly held means more energy required to yank it off. So if we were to just write the regular electron configuration for lithium, as we did last week, 3 electrons, that's real easy. It would be 1s2, 2s1. So if I look at this graph, I know that this is the electron configuration because we already know how to do that skill. If I look at this graph, which of those 2 peaks represents 1s2?
The one around the 6,000.
The one around the 6,000, for 2 reasons. It's closer to the nucleus is first, and also if it represents 2 electrons instead of 1, it is twice the size of this smaller one. So this one represents 2s1. This is half the size because it has half the number of electrons. So that how tall the peak is tells me how many electrons I have. So there's only 2 peaks here because electrons 1 and 2 have the same energy. The first peak is twice as high as the second because it has twice as many electrons. And the number of peaks tells me the number of energy sublevels. So that's as much as I want to do in these notes today. This is enough information so that the Edpuzzle video will make a little bit more sense when you watch it. And for the handful of people who already did that video, if you want to rewatch it, let me know. I can reset your progress so you can rewatch it. Again, the Edpuzzle is a completion grade, but it's still like it's helpful to have it make more sense when you watch it. So if anybody needs a picture, take a picture of that really fast because I'm going to go back to the slideshow. Okay, so to be done by the end of the week for Sunday, Edpuzzle video 32. It's just labeled PES. You really should try and do this before Thursday's class because you're going to get a lot more out of class on Thursday if you've already watched it. Because there's like some animations that they can do in the video that I can't, that will be kind of helpful to watch. The exit ticket is going to be on the next screen. And again, if you miss it and you're watching this on video, there is a bit.ly link in the video description there on YouTube and you follow that one. There is a practice quiz to help you with the photoelectron spectroscopy stuff. You shouldn't attempt these two things until you actually finish Thursday's class, because you don't know enough to be able to answer these questions yet, and that's okay. So this week, this practice quiz is just part of the completion portion of your grade. But there is a Google Doc that is the actual graded portion, all right? And it's called the PES and Valence Electron Practice, and it is the Google Doc that was attached to the practice and application assignment for the week. Based on what we did today, you can already do questions number 1 and 2, which are on valence electrons and dot diagrams. That will literally take you less than 10 minutes, and you can knock that out and get that done today. Then there's also a new free response question for extra credit this week, if you want to go do that. And there is the exit ticket. I can put it in the chat. And again, you know, when you use bit.ly, the capitalization has to be correct, otherwise it will not work. And that's it. That's the end of class. So if anybody has questions, you can hang out. Otherwise, get the exit ticket done, and I will see you on Thursday.
Bye. Thank you.
Bye.
Bye.
Thank you. Have a nice day.
Thanks, you too.
Goodbye.
Bye, Miss Baskin. Happy Teachers Appreciation Week.
Thank you, Kaya.
Bye, Ms. Baskin.
Bye.